Cool. I think we're good to go. I think we can go ahead and kick this off now. We are going to be designing a distributed database. Yeah. All right. So we're kicking it off. We got our prompt today. It's design a distributed database taken from somebody's real Google system design interview. You got to have a distributed database. It's not going to be a key value store. We want a real proper thing. You got to specify stuff like isolation level. You got to specify the transaction support, consistency level. Okay. Yeah. I had some notes somewhere on a couple of different approaches. Yeah, I can just go ahead and break this out. This is like a little bit of homework that I did beforehand on some different so it's like if you're just designing like a general purpose database, it's like, well, are we designing it specifically for read heavy use case, for write heavy use case? And then it's like there's specific things that you need for. I feel like this is why like Spanner was created, is that specifically supporting total order under a super heavy write, a super write heavy use case, and requiring total ordering. It's kind of like a use case of its own. And so that's some approaches for that. Otherwise, there's variations of this. And so the first thing I would ask is like, hey, is it for a read heavy use case, a write heavy use case, or does it have to be general? And in general, most use cases are actually going to be read heavy. And so that's why I think that the B-tree approach that's taken by DynamoDB actually makes a lot of sense, is that in general, your database should be read heavy. Because I mean, like, why are you going to write data if you're never going to read it ever? So for example, on Amazon.com, if you place an order, it's going to see multiple reads, at least by the seller, before it shows up on your page most of the time, or a couple of different services are probably going to read that record and along the way. So I think, and then it might be modified a lot. LSM trees are bad if you are going to do a lot of updates as well, because of the tombstone thing from Cassandra. So I'm going to be taking a little bit more of this approach, but I guess we can go ahead and write down a couple of different variations, then I can open up for any questions from people before we try and dive into the diagram. So there's the read heavy variation, 2, the write heavy variation, and then you've got 3, total ordering and heavy writes for ticket master, or like our flash sale problem. It's like there's certain things that are just very tailored for this like stupendously hard use case over there. I think I'll start with the read heavy one. I should capture that too. Most use cases are read heavy. So that's another reason why we should start with the read heavy use case, is that it's the most common one. Yeah, so for this one, read heavy, I can just go ahead and paste all this actually into the text file that I'm going to have I'm of course also going to have in our Discord channel afterwards. I still need to make that for the machine learning problems I did earlier this week. Okay. Yeah, there we go. All right, any questions before we go ahead and jump into the diagram? All right, looks like we're good to go. So we're going to start off with the read heavy use case. And for that one, I think it should be, oh, there we go. We got a question. Can you use dark mode for Excalidraw? No, I haven't used that one before. You can turn down the brightness on your screen. So you can just pull down that, or it's, what is it, F3 or F4 on a laptop, or on a phone, you just pull down the thing at the top and you can drag it to the left and it'll help a little bit. Okay, let's go ahead and start with the read heavy use case. B trees make sense for read heavy. they're good for updates. There's, what is it, the von Van Boa layout or whatever, where for B trees you can optimize the size of the pages getting pulled out of the hard disk to the fit with the cache a certain way. And it's just more effective with the reads in certain ways. And then single leader. So you might be wondering why single leader? It's actually not to help with failovers. It's actually primarily for write conflict handling. Is that when all of your writes get routed to the same singular thing, it can make it a lot more easy to, you would not have any write conflicts, at least for key value access. This simplifies things for handling write conflicts, at the trade-off that you're not able to scale your write operations up as much. So if you have a hotkey that's so bad that you're getting 100,000 writes per second to a single key, it's just not going to work here. It's just not going to work under single leader. If you're getting literally 100,000 writes to a single record, you would be able to kind of scale it up under a leaderless approach where you have like CRDTs or something. But again, when you're doing like 100,000 writes per second to a single record, it's like maybe you're just not doing your use case properly. Maybe you just haven't set up your schema appropriately for the use case, and you need to be doing something else. So I mean, there's limitations just how high you can scale in certain aspects for single leader, but under a general approach, single leader is going to be fine, and you're not going to have to worry about concurrent writes or write conflicts. And then I want to do snapshot isolation, multi-version concurrency control, probably version vectors. I'm going to aim for sequential consistency. And so in order to do that, I think these are things that we're going to do for internally on it. So it's going to look a lot like our each partition, each node is going to look a lot like PostgreSQL. So let's go ahead and jump into the diagram a little bit, and I'll start drawing what I'm thinking here is you basically have a bunch of leader nodes that are PostgreSQL, just like manually partitioned PostgreSQL shards is kind of how this is going to look. So we're going to have like a couple of those. Each one's going to have, it's going to be a NoSQL database. I'm not going to support multiple, I'm not going to support multiple tables. So I should maybe capture what I'm supporting here under variation 1. So these are my generalized notes up here. So I'll do that. And then I'll say general notes. Oh, there's a question. Okay. Can you explain what's total ordering briefly? So total ordering is when you need to capture the ordering of every single record relative to the others. So like, for example, if you're having a flash sale and there's limited inventory, only like 100 orders get to have some special deal, like the first 100 customers get an iPhone for free. You want to know what the first 100 customers are. And so then you're going to need to have an ordering that would ensure that the first 100 customers are known. And another thing that's important here is the concept of fairness of detecting who those 100 customers are and getting the timestamp properly. I'm going to relax our sense of fairness a little bit, which means that we're going to have, that's why I'm going for sequential consistency, is that then we don't have to do full-on linearizability, which is really hard to scale. But it's ordering all the records of the database for flash sales. For example, so it's making sure that all of your records are in a specific order, or all your transactions happen in a specific order. And fairness is going to be an important concept for that. And I'm going to use relaxed fairness. Or weak I was reading this book called Specifying, what is it? The one by Leslie Lamport, Specifying Systems. He has a chapter in there, or a section on weak fairness. I'm going to be using weak fairness, which means sequential consistency instead of linearizability. Because when you have a request coming from a guy in North Dakota that's using a dial-up connection, and a guy that has what is it, a gigabit connection that's just in Seattle, like 100 feet from your data center, that's going to be a couple of seconds between when their requests hit you. If they send them at the exact same moment, physically on the earth, there's still like one of them is going to take a couple seconds more than the other. And so then why do you really care that much about making sure that the requests, when they hit your nodes, are in the exact same ordering, and they respect the timestamps of when they hit your database? That's already a little bit of an unfairness between them. And all you can do with linearizability is make sure that those on their own are sorted. And so with my weak fairness, I'm going to let them go ahead and get disorganized a little bit. And all it ensures with sequential consistency is that there's the same total ordering across the board, but it's not necessarily fair. There's a couple of questions in the chat. I like this first one. There's actually multiple there. Eventual consistency is not really a thing, actually. It's not really a thing. What you want to look at is jepsen.io/consistency is a really, really nice diagram for what you want here. I'm going to go ahead and pull it up. Here it is. So strong consistency is linearizability, and then weak consistency is actually weaker than this one. And between those, you have multiple levels of there's read your own rights, which is I think that's like strong read consistency on DynamoDB. You don't even get that with eventual consistency because you can get stale reads. And then you've got causal, which is what Cosmos DB supports, and what makes me a huge fan of Cosmos DB. It's just very cool. I think Reoc also supports this. And then you've got sequential, and then you've got linearizability, which is strong consistency. So you really got multiple. You've really got multiple layers there. Let's put a little dash like that. And cool. So another comment there, solves many problems of eventual consistency, but is slightly less performant. Oh, okay. So that was still just kind of part of the first question. Okay, I think I've tackled all of them. Yeah, so I want total ordering, but I don't care about fairness, just because it's like you still have that issue of North Dakota versus Seattle or New York City with gigabit connection. So it's like, why do you really care about linearizability at that point? Okay, so sequential, I'm just kind of doing PostgreSQL with some snapshot isolation, which is what's built into there, version vectors. We're aiming for that. We got these shards. And so you're going to have, you also need to have this thing that captures which of the shards is responsible for what portion of your partition. I'm going to have this, also you have to figure out which node has that, is the leader for the partition that you want. So you're going to have this thing out front, which will be the request router. And that term request router is actually brought up a little bit. So request router is actually mentioned in passing somewhere within DDIA. It's the request router. Tracking which node is responsible for what partition, or like where you're going to send a particular primary key to. And then you've got your client, which is going to be some other backend service hosted within an EC2 instance. And so this would just be EC2 instance hosted service. Make this a little bit There, now it looks a little bit less funky. And I'm very pedantic with my diagrams. I'm so sorry. So you got this request that comes in, and it's going to have to figure out what node it is. And with Cassandra, it just kind of, the request router logic, I think, is actually hosted on the nodes themselves. But over here, it's actually going to look it up in this key value store. It's you can use etc. D for strongly consistent key value store. And it's not going to change like at all. It's hardly ever going to change. You might think it's weird that we have a different DB as part of our own DB. This is just a KV store though. And they actually do total order broadcast themselves. You just need a KV store though. So this is distributed as well. And then it's going to store lookups for what partition we want. I guess we could even just do Redis and have it like on disk internally, and each request router could have a copy of it. And then when you're doing rebalancing, it's going to have to do an update over there. But you're going to have this KV store that'll route, it'll figure out which partition owns your KV that you're trying to find. Yeah, and so then it looks it up, and then it can go ahead and route your request to the proper shard. It'll be like, oh, okay, so you're looking up this key value. It's going to involve this shard, and then it'll return a response. Or it could be distributed key value lookup, and then it might have to hit all the shards. I'm not sure. So that would actually be some of the query planning logic. So this is going to be the coordinating logic over here. We're figuring out what partition is going to own what. An alternative is to have that host directly on the individual shard nodes instead, which I think is what Cassandra does, but we're not doing that. And so then it's going to look it up on that shard, and it will return that back. And that is just for a read. What about writes? This is just for how you handle the reads. And you would probably want to have some kind of redundancies. This is just talking about variation 1, and we want to talk, this is the read scenario for that. I do not like the sloppiness default thing that's built into Excalidraw. Make sure all this is large, and then there. Okay. And now I want to go over the write scenario, which is very important for the conflict resolution stuff. So again, you're looking for updating one specific thing. It's I'm kind of talking about this specifically within a key value context, and kind of maybe hand waving key range. Well, you don't do key range writes. You don't do a key range write. You don't really do that. You can do like a batched up operation or a transaction of writes, but like when you're doing a write, it's just for like one record. So again, it comes in, you look up where it is, which partition is going to handle that write operation. And then since it's single leader, this is where it really shines through, is that there's only one node that could possibly handle it. And so then you won't have to have any kind of write conflict logic. You can just have this set up to the linearizability setting in PostgreSQL or something. And then when it's linearizability, you already have a total ordering, and concurrent writes are impossible when you have a single machine of PostgreSQL set up to linearizability. Concurrent writes are impossible, which means no write conflicts. It's serializable isolation level. So it's only when it's leaderless that you're able to have that. When it's leaderless and you have the serializable isolation level, you can still get concurrent writes. But since it's single leader, you just cannot get any concurrent writes here. It's a single partition. But when it's one node, you have this issue where, what if the node crashes? And so you're also going to have at least one replica. You need at least one replica for it's a synchronous, what is it? Read replica for failover handling. It's the backup. So PostgreSQL backup read replica. You want to do synchronous replication. So you're doing your write over to here. It's not going to return a 200 success until it captures it on at least that one node. And we're still going to have to figure out failover, but that's not why I did single leader with simplifying the failover. It was specifically for the write conflicts. You're going to do synchronous replication. So that way we're not going to have any issues with losing all our data when we have a node failure. And then you can go ahead and return the 200 response. And you can go ahead and tell the client, yep, thumbs up, we've recorded your write operation. You might even want to have a couple here. You might want to have another leader, another follower replica. And then depending on whether you have it set up to, what is it? Depending on your settings for consistency, you might even be able to have this as an async replica and do like gossiping instead. You at least want to have, you need to have at least one read replica that is strongly just synchronous. You need to have at least one synchronous replica. And then over here, you can go ahead and have like gossiping or something. If you allow the eventual consistency. How it works with DynamoDB, if you want to have, if you do a strongly consistent read, is it actually hits the leader directly. I can go ahead and talk about that in a second. Go ahead and give me a minute here, though. I'm going to say gossiping. I'm not 100% on this. This is a harder question. And then we're going to say these are the follower nodes. And then we got our leader node. Let's give myself a little more space here to work with. We're going to have follower nodes. And then we have our leader node for a partition. And I should maybe go ahead and capture that this is a partition. So we're going to label that partition 1. We're going to say leader node. And then we have our follower nodes. And at least one of those has to be synchronous so that we have a failover. And let's maybe drag this out again. And I want to label the other partitions a little bit. I'll have partition 2 and partition 3 down here. So hopefully you guys are following along fairly well so far. Partition 1, leader node, follower node, and then I can illustrate the strong read consistency versus normal consistency level that DynamoDB has. Is that I'm going to go ahead and kind of copy this. We'll have let's actually, I want to do this is going to get really messy, and it's just illustrating a concept. So I need to have it off to the side where it's not going to be as, it's not going to make us look as convoluted. So I'm going to have a copy of this. I just want to illustrate that strong read consistency concept in DynamoDB. So normally, under the normal replication, let's go ahead and have it down below. And we're going to drag. Let's go ahead and drag it over here. So you have a request from the client under normal mode to the request router. And they don't need a strong read. They just need an eventually consistent read. And then it can just go ahead and look at this off the request router after pulling it in from the KV store, which might be cached. And you can do some kind of cache invalidation logic, or It's going to look up which partition to route this request to, though. And it can return the response, which is going to be possibly stale since it might not see the latest read. And this is how eventual consistency works. And then you'll see the response. And then if you want a strong read consistency, then you'll have this. And what they do is they have it go just straight against the leader node instead. And so that's why those strongly consistent reads are twice as expensive, is that I think they also have to scale up the leader nodes as they shard it even more, because now there's even more traffic that's going to be hitting this directly. Because then they might need to shard it a little bit more. And it's twice as expensive, and it goes right against the leader node. And as we'll get to later, for the ticket master scenario, if you're tailoring it specifically to that, I would recommend the single leader approach like this, and you're just going to shard the hell out of the leaders in order to make sure that you can handle the scale. But yeah, that's how I'd scale it up for that. I got a question in the chat. Does it make sense to have a separate coordinator for all the shards like Zookeeper, or does the request router handle coordinator? So that's actually what I have over here. So etc. D is an alternative to Zookeeper. They're both strongly consistent KV stores. I've heard etc. D is actually what is it? Kubernetes uses. And then etc. D, I think etc. D might be, I don't know if Google made it or not, but that's why I went with etc. D instead of Zookeepers. That I've just heard of it being used as a strongly consistent key value store. There was a Googler that joined my org at work too, and he used etc. D for a thing. I obviously can't go into a lot of depth about the context around there, but I've also seen it personally used for doing key value store stuff. So Zookeeper, though, that's basically what I'm doing over here. Or does the request router handle coordinating the shards? Yeah, it's okay. Yeah, I think I've handled all the question. Now we can go back. I handled my case. We can go back to, whoops, the toolbar should not be there. There we go. So I've handled this detailed thing about what a strongly consistent read is versus a eventual consistent read. I'm going to go back. I've talked about how we should have at least one synchronous read replica. I think that's really all I want to talk about for variation 1. Oh, failovers. Okay. Failovers. You need to be able to detect a failure, though. So with a failover, you need to be able to detect. So now we're going to talk about handling a failover. So failover handling. So 1, detect failure. And then 2, there's the leader election. So do the leader election and switch over to the new leader. So for detection failure, this is in from Database Internals is the name of the book. It has a nice discussion of this. What you want is phi cruel, and it's just it picks up on the average response time, and given whether a response from the shard is taking longer than you would expect. That's how you determine that a failure has occurred, is that it has taken longer than the average response time by a certain confidence level. So you have like, what's it called? A Poisson distribution of your responses, possibly. You can just like look at confidence intervals of how long it takes. And then when it's over a certain time, or you can even have a hard-coded cutoff of like 15 seconds. Like, hey, it's been 15 seconds and I still haven't heard from the leader. Let's go ahead and move on. You'd actually probably have it like way lower than that, given that it's within the same data center and it's like, it's the database setup. It's like a managed database. And so you could probably even set it as low as like 100 milliseconds, possibly, because it's like within the same data center, manually handled infrastructure. So you can say like hard-coded cutoff 100 milliseconds, it hasn't responded. We're going to say that it's dead. We're going to have that detection run on the request routers themselves. So the phi accrual algorithm runs here. On the request routers themselves. For Cassandra, I think it has that on the leaderless partitions. Like this whole thing is just pulled directly into the individual nodes. And so you're not seeing back from it. And then you haven't heard your response back. And so then you know of the synchronous read replica. And so then you would just update your KV store to the new leader. Have our steps is 1, detect the failure, 2, promote synchronous read replica, in your key value store. It's just going to overwrite who the previous leader was. And then, I mean, you could even return a 404 or something while you're handling that. And it's like, hey, we're having you're going to have some kind of degraded availability, I think, when you're doing that. There's going to be a performance hit. There's at least going to be increased latency, degraded performance, perhaps degraded availability while you're handling the failover. I'm not familiar with the actual failover, the actual leader election, but in our case, I would have at least one synchronous read replica, and that is our failover algorithm, or our leader election algorithm. That is our leader election algorithm. There's we're doing the ring method. We're doing the ring promotion method. There's this one where there's just this ring and you're just circling through the ring for who becomes the leader next. That's what we're doing here. Let's give ourselves more space. And that's in our KV store. And then, yeah, so this just kind of gets moved over to, let's maybe like draw an X like that. And then again, we're not really interacting with partition 2 and 3. So then we're going to take our follower nodes. Let's go ahead and copy paste that over to here. And now our read replica is going to go there. And it's going to need a new read replica. And now our request is instead going over here to what was formerly the synchronous read replica, and instead our request is going to get handled over there. So the Postgres backup read replica is now promoted. It's now a full-on leader node. then it cannot properly take over as a leader unless it knows to start doing that synchronous replication to somebody else. So there's going to be a new synchronous read replica. Oops. Newly synchronous, and it is a follower. Yep. Okay. So that's my handling for failover. Rebalancing is incredibly crazy. It's going to do some kind of shuffle over there. You would have this new thing get introduced. It's going to start pulling over. It's going to do gossiping or something. It's going to pull in a bunch of stuff until the Merkle tree is good to go. And then you would go ahead and update the KV store to like start routing more, to start having it route requests directly there instead. And it would need to become synchronous, and then you can go ahead and flip the switch and have it like become the leader itself. I wonder if I should actually try and draw this. I can kind of I'll take a shot at drawing the rebalancing. I'm not going to, there's a big chunk that I'm probably going to just leave out. I can go ahead and maybe talk about rebalancing from introducing a new node though. Whoops, I don't want to display the toolbar. We'll have rebalancing after new node added. And we're done with that. We've still got that. We don't need our little thing from the failover. Good. Nope. Not gonna do that. Station 2. Got this. We've got a new node coming in. We got our new machine. It's going to start out with, we've got these PostgreSQL copies, these like machines that we're going to have over here that are going to have partition 4. We're going to have a new partition 4. And you're going to have it, you're also going to have these for partition 2 and 3. It might become the leader of a couple of things from each node is the leader of multiple. Each node will have like 100 partitions on it or something. It's the lead of maybe like a couple of them. Well, it can also be the leader for, it can be a follower for some of the other partitions, but each node can be a leader of several partitions. I'm not going to have it where the lead nodes can also be followers of certain partitions. I guess I'll just have it as a leader of multiple partitions, but not a follower of any. Which I think is different than how it actually works in reality. I'm doing something different because it's more simple to understand. And that's how I'd actually do it in an interview, because it's like you can't possibly have like the full proper implementation of all these things drawn out in a single interview, I feel. So you have this, you got your partition 4 over here. You're not going to have like a lead picked out. I think you just kind of want to start having data like pulled over through gossiping or something. Have it curved. Let's go ahead and copy paste this. And we're having both of these copy data over. And then when it's good. It can become a synchronous read replica. At some point, you turn it into a synchronous read replica of the partitions that you want to have it become the lead of. So we have our steps. Is that one, start gossiping data over to the new machines. 2, the machines become synchronous read replicas for the partitions that they should be promoted to leader of. And then 3, promote one of the machines to leader in the KV store. And then 4, it is now being routed write requests. So that's our steps for that. It's gossiping. And then at some point, let's say that there's 3. And then at some point, we're going to have one of them and they're going to get promoted. And it is going to become the leader machine. And it needs to have at least one synchronous read replica that it'll be doing the writes with. It needs at least one synchronous read replica. And again, needs updating the KV store. And then it can go ahead and start doing the writes directly there. Get your response back after doing your synchronous read replica. Then you can go ahead after the synchronous replica writes it, you can do your 200 response back and return that over to the customer. So that's rebalancing after a new node is added. We are actually 50 minutes in. I'm really happy that I started with the read one and went in depth with that because this is already taking a lot of time to cover. You can maybe talk about, I have no idea how to make it so that it is, so you can have these set up as linearizable, and then how that becomes sequential consistency, a little bit beyond me, I think. But inherently, if you have one node as the leader and all writes hit it, then that node internally, I mean, its clock is synchronized with itself. You only have one clock to synchronize there. So it's just inherently synchronized with itself, and you don't have to do any kind, you just will not have concurrent writes because it's linearizable or serializable. All the writes have to be in an order. They just have to, because that's what linearizability is. And when it's one machine, one clock to synchronize with itself. And so I guess that's how you make it sequential at minimum. But the issue is that if you have a key range query where you're hitting multiple machines, you know, the writes are not synchronized across them, but you would still have a total ordering of all that written data. And so I think it would be sequential consistency, or at least causal. It has to be a very minimum of causal consistency if you have each machine set up for serializable isolation. It's a bare minimum of causal. I'm fairly certain it's at least sequential, but then in order for it to be linearizable, I think it has to satisfy fairness, which we're not doing. I don't think we're satisfying fairness. But with serializable isolation, I think we're there. Okay, and then I guess we can talk about leaderless and kind of like how, yeah, we can talk about leaderless a little bit and why you're just going to have, I would just not shoot for sequential consistency here because of that concurrent write conflicts issue. Yeah, let's go ahead and have variation to leaderless for heavy writes. And I would not have this if you want total ordering. You should not. Only causal. Because of that right handling issue. So again, we're going to have this, and I guess there'd be like multiple leaders for each thing, or you can just merge the request router again with the partitions itself. I'm going to find something good I can copy over. Okay, yeah, all right, this will work. Maybe I should just go ahead and copy this over. Yeah, that's what we'll copy over for this one. There we go. Okay, so any of these nodes can handle if you have your storage, so there's so much data that is what you need for sharding it. That means that each one is not going to have the full database. Each one is going to have a certain set of partitions that it is set up for. So let's go ahead and draw. I'll go ahead and have that explained a little bit. And I guess the request router could still store at least a list of which nodes for each partition. Let's go ahead and maybe talk about the schema here a little bit. Is that you got like partition 1, partition, let's have 1, 2, 3, and 4, and then each machine is only going to get 3 partitions. So, oh. So we have partition 1, 2, 3, and 4. And then this one will be on machines 1, 2, 3. Next one will be on machines 2, 3, 4. And then we have machines 3, 4, 1. And then we'll have machines 4, 1, and 2. So it's just a mapping of which machines own which partitions. And each of these machines are leaders for that partition. And so let's say that for partition 1, 1, 2, and 3 are all, I'll go ahead and label these as machines 1, 2, and 3. 1, machine 2, machine 3, and machine 4. And so let's say that a write comes in for partition 1. So we'll say that there is an incoming write for partition 1. And so I'm going through variation 2 with the write scenario. Okay, so you've got one write coming in, and it's trying to write for partition 1. Let's go ahead and say write against partition 1. And you have that. It's going to get routed over here. And you have another one right at the same time. It's a concurrent write. It's getting routed over to here. Since they're different machines, their clocks are not synchronized. Just they could have the exact same millisecond or nanosecond for a request. It's actually, if you're going to be doing this, you're probably just going to use a millisecond time. You might just even use wall clock time, which is not monotonic. And so it's it'll just be a millisecond time. And if it's over 1000 TPS, that inherently means that you're going to have more than one write per millisecond. And so you would, anytime it's over 1000 TPS, that means you're getting more than one write per millisecond. And so you will have concurrent writes if you're using Unix epoch time. So they hit at the exact same time. And so then you have for primary key value of EF ABC -123 EF ABC at 167 000 5,000 milliseconds. Do a write operation, and we'll have the exact same thing right over here. Let's even have this look like we'll say 347. There we go. So they're getting written at the exact same time. And then when they're doing their gossiping or whatever, and so then they're going to do the gossiping across the partitions. Make this like that. Oh, okay, so it's dashed, and we're going to have another one. Whoops! Oh God. Sorry. Have another one, just like that. I'm going to label this as gossiping. And so now it knows about the concurrent writes, and it has to do something to merge that. And so let's go ahead and say concurrent writes is detected. Now we have to do a write conflict resolution strategy. They could even be slightly far apart. So actually, this is what it is for DynamoDB and Cassandra, is that let's say that they're like that. And so you can just do last write wins conflict resolution. Under last write wins, you just take the write from machine 2, and that becomes the value on both machines. And then if you with Cosmos DB and Reoc, you can do something different. And so if you have like a counter, so this is also where CRDTs are very valuable, is that instead of having both, just having one overwrite the other, and then you just have a lost update, you would just instead have both of those counters would successfully get observed. The count on both would get successfully observed. But you could still have that issue with the dropped ACKs. An ACK off of this coming back can still get dropped, and then you would have a double count. Let's say Cassandra does this. With Cosmos DB, and if I recall correctly, Reoc, you can specify the conflict resolution strategy instead of, with Reoc, it's a default of last write wins. Default of last write wins. Okay. And then I don't want to do ticket master, but it would inherently just be this. You would just shard the hell out of it. And so I guess I'll just write that, and then we can go ahead and wrap up the session. Is that ticket master is basically just going to be variation 1, but shard the absolute fucking hell out of it and use LSM trees that stick that in my notes up above, or no, I don't need to do that. For this scenario, basically just follow variation 1, but shard the hell out of it and use LSM trees, which are more performant for heavy writes. LSM trees, shard the hell out of it, fewer read replicas necessary. Can't use LSM trees. Was there anything else? It was, yeah, and you need to use the linearizability isolation level. Serializable isolation level on each leader node. And I'll do that. I'll just copy paste that. Say the same thing. And then we can wrap up this session. Master and total ordering is necessary. Just do copy variation 1, but hold on. Use LSM trees. Serializable isolation level. And fewer read as necessary, or basically none. You just need the synchronous one, and that's it. Cool. All right, that is all I got for you guys. Any questions before we end the session? So go ahead and zoom out for people to look at, in case they just go ahead and click to the end of it. There we go. Zoom in a bit more. Okay, yeah, we can go ahead and wrap it up. Thanks for watching. I hope you guys enjoyed the video. I will see you next time. Thank you.